Welcome to the second last lecture on vehicle motion planning. So today I'm embedding this topic a little bit more. I talked about attractor dynamics in the last couple of lectures. Our particular approach that we developed that is somewhat continuous with our work on human behavior and neuroscience. And today I want to link that to the robotic field of how people think about vehicle motion planning and robotics. And I'll first introduce some general terms so that you can sort of orient in the literature, so which sort of positions our approach within the literature. And then I'll take you through a few approaches that are current, that are used by a lot of people. And in one case, the potential field approach, I'll actually relate it in detail to the attractor dynamics approach that we've discussed a lot. In the other case, I'll just mention this a little bit more as a matter of information. So let me first maybe go back to defining what is meant by vehicle motion planning. So it's planning of the paths of vehicles in the plane in a 2D world. Of course, for cars and so on, there could be elevations on in 3D, but locally is always 2D. So it's about avoiding obstacles, anything that sticks out from the surface, from the 2D surface at any moment in time, and going toward targets. And under some conditions, there are additional constraints like planning a path that goes through particular points or that achieves particular orientations, particular points. And I'll generalize that over the lecture and look at things like docking, orientation, controlling orientation in some way, and maybe moving along a path, for instance, so staying on a road and things like that. So for first, the important maybe conceptual issue to know is that this planning problem as such has to do with constraints that are either holonomic or non-holonomic. So those of you who know a little bit about robotics in general, maybe classical robotics, might already have heard that term. So what we're talking about all the time is actually about vehicles that have non-holonomic constraints. And that means that there are fewer variables that can be freely chosen that you can give a value to at any moment in time. Then there are variables to describe the physical state of the vehicle. So for the vehicle, the physical state of the vehicle is characterized not just by its position in the plane, that will be two variables, but also by its orientation in the plane. So it can achieve actually any position and any orientation in the plane, but you can actually control only two things, like the two motors, for instance, or in a vehicle like the steering angle and the velocity you give to the wheels. So only two things to achieve any of those three things. And so that really means that you are achieving the third thing by applying commands to these two degrees of freedom with a particular history. For instance, arriving at a particular position from a particular other position, and that then controls what your heading is when you're at that position. So this problem is relatively trivial for the kinds of vehicles we were considering because they can rotate on the spot. So those have very simple strategy. That is, if you want to achieve a particular orientation of the vehicle, all you have to do is go to the position and then rotate on the spot. That will be a very simple way of doing it. Or generally along a path, if you want to turn around a corner, for instance, you can go there, stop in terms of forward velocity, and then turn on the spot. But it's a much more general problem about which there is a lot of work to deal with non-holonomic vehicles that are that cannot turn on the spot and where the history dependence is more severe. So the cars that you're all familiar with are like that. They don't turn on the spot, and therefore maneuvering a car, for instance, into a parking place like curbside parking isn't quite so trivial, as some of you will know. You can't just drive into the location and then rotate to be parallel, right? You have to make a particular history of moves in order to get the car there, and then also to get it out of that location again. And there are very good algorithms for that. There's good mathematical theory for that. As you might know, autonomous parking for cars actually works very, very well. There's a perception problem of knowing, where the curb is and how open it is, but it works very well, better than human. In fact, one problem is that then humans might find it hard to exit the parking spot. And in many legislatures, you're supposed to do that as a human because you're not supposed to autonomous drive yet. And then the car might drive parking too close to other cars for you to actually manage. So I'm not covering that, but there is a whole literature on that that also often runs under the label of motion planning. So that's just a concept and to be aware of it. And so when we talk about motion planning, we're talking about this planning layer here, right? The planning of the movement that is built on having some knowledge about the movement and that knowledge about the environment, and that knowledge in autonomous robots would come from sensing. In classical robotics would come maybe from having a world map and knowing where you are in the world map. And I'll next week talk a little bit about how you could know where you are based on sensory information. And then, of course, there's also the idea that you actually have to physically bring about the planned movement, the control. And you will have to do that, you will have to estimate what it is that you actually did. And we also sort of glossed over that, but that's part of the problem. In a lot of the kind of robotics I'm talking about, the control problem is relatively trivial in that you have very good, well, controllable motors and work on a factory floor where there's very little slip and so on. So it's not a problem that's anywhere near as difficult as it is for robot arms. So this sounds like the Senseplan Act that I mentioned initially, but it doesn't always have to be that way. In fact, some of the approaches I will be talking about are used in what is called reactive autonomous robotics that is more behavior-based, where you really think about a close integration from sensing, planning to control. I'll show you that. So another two concepts already referred to reactive here. So global versus local. So local path planning is what we've been doing so far, or vehicle motion planning. And that means that it's based on information that is available to the robot about its vicinity as compared to information that would be global about the entire environment. So when I showed you how this simple robot we built in Marseille goes, finds a entry into a particular arrangement of obstacles, then that was based purely on it always just measuring distances and didn't have a plan to know where the door is, right? That would be an example of where local is really different from global. Global would mean you have a map of the world, and that map extends, for instance, to the target beyond what you can currently see. And there are examples, and I'll give you some examples of global motion planners. That a lot of classical motion planning is global in that sense, assuming you have a map. Somewhat related, this idea of reactive versus really planning. Reactive is often what local approaches are used for, because reactive really means that you're responding in planning to sensory inputs. So reactive also means that you can update your plan any moment in time because you're just acting at every moment in time given on the sensory information you have. And our approach in this sub-symbolic kind of approach is certainly reactive in that sense, right? It's able to update the plan in the sense that the attractor shifts. So we showed how when the attractor shifts, you're tracking that attractor. So it's a reactive approach. In that sense, it's a bit odd perhaps to call it even planning. It will be sort of online planning, or on-the-fly planning. While motion planning would then, in a more stricter sense, that's not reactive, would be planning the entire trajectory or path. Trajectory really means that you're also planning the time course, and path would be just a spatial course, and you can run through it at any desired speed. And there are a lot of trajectory planning approaches that are really doing planning, and for instance, some of them actually simulate different possible solutions beforehand, sort of try it out and then search through the space of possible solutions to find one that globally is good, that reaches the goal, and so on. So that's also a somewhat different category of planners. Another pair of concepts that's often used is to talk about exact versus heuristic approaches. So exact approaches would be ones for which you have some mathematical guarantee that a plan will be generated when one is possible that does fulfill the constraints. While heuristic would mean that it is a plan that is based on some hypothesis, some ad hoc method, and it is likely to fulfill the constraints, but it isn't really guaranteed. There can be exceptions, exceptional collisions, or exceptional blockages, for instance, where you wouldn't achieve the goal, even though it's possible. And most approaches that are used in practice are, of course, heuristic, because it's actually a very strong requirement to have an exact approach. There is a field of vehicle path planning that is about exact solutions, where you usually have to make some assumptions about the world. Some of these solutions use certain kind of mathematical idealizations. For instance, there's a famous approach where you're using essentially Poisson's equation, where you write down a potential where you can guarantee that the only maxima are the points that you specify as maxima, and so they're not artificial maxima or minima, and so in some sense you can prove that you will fulfill the constraints. So that's really more for the mathematical theory of that. And then there's also a difference between continuous state space planning, which is what we've done, of course, versus grid states or discrete state space planning. Sometimes discrete state spaces are simply just discretizations of continuous spaces. And for instance, reinforcement learning very often is based on that, where you have different cells in your state space, different positions or velocity values and so on. And you're really just planning how to go from one grid point to the next neighbor grid point. And that's the discretization is useful because the algorithm for this form of planning, for instance, reinforcement learning, which some of you might know, requires discreteness. And you cannot actually, in practice, make the grid size very small, because the number of possible choices explodes combinatorially when you increase the number of grid cells. So it's essential that they're discrete. The actually more interesting branch or variant of that is when it's not just a grid, it's not just a sampling of a space, but it's something that is inherently graph-like. So where the different discrete entities will represent things in the world. For instance, you could have a street map where there are only certain crossings, or only certain points where you can actually make decisions, and where therefore it's natural to think of navigation as going from decision point to decision point. So any plan, any point at which you then have to make a selection, and then you would have a state space that has a graph-like structure. And then also some of the planning approaches are mathematically formulated in that setting, for instance, searching for possible paths through a graph like that. So I was already hinting that.
I have a question.
Yes, please.
Referring to the last slide. So our approach we analyzed with the Gaussian function. This is also heuristic, I guess.
That's right. It's heuristic.
Okay.
Even though it's mathematically formulated, there is no guarantee, it's not a theoretical proof that when these different contributions are combined, they always satisfy the constraints. When we're trying to analyze the situations that would most likely challenge the approach, like two symmetrical obstacles, but for instance, there could be cases. In fact, I can tell you an anecdote that the student who developed some of this work, Michael Dose, found a violation of the constraints, which initially puzzled me, because I actually asked him to reproduce it for me, and then he showed me on his simulator, and it turned out it was only one point in the plane where this was possible, and it was a situation where the robot was encircled by obstacles of certain distance, and then all the contributions canceled and would collide. And that was a real failure of the approach. Of course, it was also really impossible for the robot to get into that position, right? Because it was encircled. How do we even go in there? Because if the encirclement had to have exactly a certain curvature for the constraint violation to occur. So that was an example of a failure of the approach, even though it was not very relevant in practice, because it would be unlikely or impossible to get into a situation like that. Okay. So I mentioned this in the introductory lecture, this notion of Senseplan act versus behavior-based. And it's not parallel to reactive versus planning necessarily, because you can have a Senseplan act kind of idea and still be reactive by simply having the sensing and the model being very simple. And some reactive planners are really like that. While the strict behavior-based idea would be that every constraint would have its own sensory input-output function. So like obstacle avoidance versus target acquisition would have their own sensory paths. And in the examples I gave you for the so-called subsymbolic approach, that is well approximated as a behavior-based systems here in this bottom sense. And the combination of the different constraints was simply just by superposing the contributions to the vector field. And I'll show you today another example, and it goes into this direction. But there are, for instance, the potential field approach, which I'll be using, is sometimes used here in this spirit, for instance, by Arkin. I'll review that, but also sometimes here used in this spirit, where you're taking a world model and finding in the world model the plan. So you can't really say that something like our approach of the potential field approach is necessarily in this picture or in that picture. It's more a question of how you actually embedded in a system. So where does the sensor information come from? Is it general purpose sensor information or special purpose and so on? Good. So the examples I want to show you, I very briefly talk about classical planning, even though that's a huge field. I'll talk a lot about potential field approach. I'll present this particular approach because it is an early version of the attractor dynamics approach. And I might talk about the dynamic window approach if I still have time left. I introduced some additional stuff here in these first two. Actually, I'm not going to talk about that, planning, which is part of the classical approach. So the classical planning is here just as a reference, so that you know that it exists. It's a big field in the sense it's a sort of field of applied mathematics. There are big books about it, and it is sort of there. The vehicle planning is just a special case of more general planning problems. There is a whole field of artificial intelligence that deals with planning, which can be also planning of other things like planning production schedules, planning in logistics. Not as necessarily in a 2D world of configurations, could be a much higher dimension state space. For instance, let's say these Amazon warehouses where robots do actions, they actually use classical planning, but it's not just planning the paths. In fact, the paths are relatively trivial because those robots move on an imagined grid, just horizontal, vertical, or east-west, east-west, north-south. With obstacle avoidance and so on, but it's planning in the sense of optimizing the time it takes for particular objects to be transported to particular locations and all the conflicts in it and so on. And so this is a big optimization problem. And so this classical global path planning is embedded in that literature. There's some really good books about it. The Tomes is a classic book in 91, standard reference, and it's actually available online now, I believe. Or was it the Laval? I don't remember. I think the Laval, which is a more recent book, there's a 2010 edition, maybe even more recent editions. I think actually this one is freely available online as legally available by the author. It's not, there's very little overlap with what I've been teaching, but if you're interested in that, then you kind of look at that. So they often frame the problem as one of objects that have particular geometries. So for instance, polynomial worlds, so piecewise linear surfaces in the 2D world. And then your vehicle is also a polygonal system like that. So like a rectangle or some other shape. And then very typical class is to move toward a target configuration of that vehicle, not just the position, but also its shape, how it fits, while avoiding obstacles. And so that's a special, special case of much more general problems. And essentially, what people do is frame this as a search problem. You're searching for a path which is a function in configuration space, or function of a parameter which you could consider time. And some of the approaches actually then sample, because that search space is continuously many paths on. There's sampling approaches where you're trying out different trajectories to some discretization and so on, and then search the space to find, in some sense, optimal solutions. So there's a large literature on how to do that. It is still a computationally expensive thing. So this is the sort of thing that is being done for robot arms. I will briefly alluding that to that in the second part of the lecture, but I will not go into the detail of that either. But I can tell you, just so that you position that a little bit, that when you do such planning for arms, as is routinely done in robot manipulation, it's actually still computationally quite costly. So it's actually not easy to do that in real time. And there are companies that offer special chips, special boards for robot arm motion planning to achieve the search in approximately real time, so you can do it faster. So it's not a trivial issue. For vehicles, it's much easier than for arms because the number of degrees of freedom is smaller.
Would
yes,
optimal control approach work in this case? So if we know all the obstacles and the target before and have a grid, we could use maybe an approach like dynamic programming. Would that work?
Yes, so there are approaches that do optimal control. Optimal control is more typically used when you are really dealing with control. That is, when the time courses are informed by control problems. That is the difficulty to have limitations on accelerations and turning rates and things like that. So because what it does is finds the time course that is optimal. Well, in the planning world, the time is just a parameter, and it isn't. It doesn't really fast to go through the arena. You can make some constraints about time not to go too fast and so on, but that's something you can do post hoc. Like you can go through a path and still vary the time, how fast you go through it, to respect accelerations, limits on acceleration, deceleration. So that's not the standard approach. The optimal control is really used at the control level, when you now want to decide how to go through, how to follow, how to track your path. Now, what kind of control signal do you need to send to do that? But it will be, so there are some, it's mostly for robot arms, not for vehicles. For some arms, you will have optimal control methods wrapped into the planning. Okay. Good. So here, this is what I actually just talked to you about. Yeah. Smoothness constraints and so on. So I don't want to go too deep into that. It's a whole field, and it has its own terminology and so on. So this is, for instance, an example where things like that are used are autonomous vehicles, where they have maneuvers like lane change and so on, and they will have ways of determining what are good paths to choose for that, and have a whole library of those and select among those libraries and so on. So they are not just doing this simple reactive kind of control that I was alluding to so far. The most prominent approach in this whole literature, I think, is the potential field approach that does have a relationship to dynamic systems approach I was referring to. It exists in different variants. It is also an approach that can be used for arms. In fact, it was invented by Usman Khatib for robot arms. There's a similar formulation by Neville Hogan. And it was made quite popular for its real successes were in vehicles. Because it actually is very complex to really realize it in robot arms. And Khatib's lab for a long time was the only one that was really able to do that. And today, the arm in the domain of robot arm motion, it is still, or it's also being used, but in the vehicle domain is very often used as the lowest level, like the local reflective or reflexive approach that is, no, sorry, reactive is the word that I was looking for. Reactive approach at the lowest level. I'll show you an example of that. And so the notion is that you find an adequate representation of your manipulator or vehicle. For instance, for manipulator, it might be just the 3D end position. For the vehicle, of course, it is the degrees of freedom, for instance, would be the 2D position of the vehicle, maybe including the orientation. And then you're in that state space, you're defining a potential field, a potential over every possible state value. And you have some recipes. So in one version, for instance, positive is values of the potential are where you don't want to go. So you go downhill, you can flip the sign and just go uphill. So if you go downhill, then you put hills into that potential where there are obstacles, and valleys where there are targets, right? And then you have some kind of gradient descent, different rules that you could use with inertia without, of always going to go downhill. So you're supposedly going to end up in the valley. That will be your target. And because you go downhill, so you certainly don't go uphill, you would avoid obstacles. You would not collide with an obstacle, because when you get close to an obstacle, it goes uphill. That's roughly the idea. So here's an example from Khatib's original paper in some state space. For instance, you would create a shape like that, mathematically described through something that would define an obstacle in the space. So the vertical is the potential. Potential is just a scalar number, right? And so you would never go uphill, so you would not go in the direction where there is this little blip here, or blop. And there are many different formulations for that. Now, I'll show you an example of that comes from the Thomas lab that is really classical planning with potential fields. So where you know the world where you have a map of the world, in fact, polygonal worlds, and where it is finding the potential around that notion. So for instance, in that particular version, what you do is define a potential by defining equipotential lines mathematically, and essentially some distance function with a lot of ad hoc assumptions how to deal with corners and so on, that will take the polygons into account and then compute the potential with some rule from that. So for instance, you essentially determine the next equipotential line by some algorithm that looks at the distance from the different surfaces in 2D, so the different lines, polygonal lines that delineate obstacles. So this is maybe a plausible sketch of equipotential lines where the maxima would be here in these dark zones, so it would go downhill from there. And you would then similarly define some target field. So you could maybe intuit it that the target, I guess, should be here. And so these are equipotential lines, in terms of going down, that would point to the target. So you would always go in this direction here, in that direction here, and so on. You put that over the entire array. There are some special tricks then, because this doesn't actually generally work. For instance, in this case, they put some bubbles around the obstacles to exempt those from this rule of going to the target, and then you superpose everything. I don't have that is actually, I think, probably the superposition already. And then the superposition, there you make gradient descent. You can perhaps see that, it may be intuitive that it goes downhill here, and maybe it goes downhill there, and so on. And so such things work. Again, they're not exact. They don't always find a path when there is one. And one of their claims to fame is that you can actually do more than just a circular vehicle. You could have like a longish vehicle and really do things like, for instance, a turn here, where the vehicle has to reorient to make it through this opening and so on. So things like that are possible in an approach like that. You could maybe get a sense for how complex that can be. I'll show you in a little while. I'll show you how we couldn't do that with the attractor dynamics approach. So something we didn't do so far, right? We did a very trivial form of obstacle avoidance where the robot is a circle, so with just a safety margin. So that's a much easier thing. So the opening is not, it doesn't matter in which orientation you go through an opening. Here it matters. In fact, the potential field approach is very flexible that way. That's why it can be extended to arms. Here's an example of using it for arms, actually, the 2D hypothetical arm, complex, just to demonstrate the power, right? It is able to find a very complicated configuration to go through this funny opening using this kind of descent. It's then in a high dimension space, in the configuration space of that arm. I'm not explaining exactly how that works here, it's just to show it that has some mathematical power. So this is using the potential field approach in a sense of an abstract planning algorithm, while the other possible way of doing that is doing a more reactive one, so where you're planning the path and obstacles are really just points, maybe with some extension of these points. And that's actually something I want to show you that is from that paper that I think you read, or I think I asked you to read parts of that, right? I think for one of the exercises, the Warren paper. That's the folks who compared the dynamical, they used the attractor dynamics approach, they call it dynamical systems approach, to fit the human navigational behavior. And they also compared, in the second part of the paper, some of you might have read that, they compared the potential field approach to the dynamical systems approach. And so that, has the same register as our approach, in the sense that the obstacles are really just points in the world, and they have some width parameter, like this would be a potential landscape for avoiding obstacles that are these locations where these little columns are. And in this would be a case where you think of this as narrow obstacles, so just a point with a little bit width, and this would be where you have a larger range that you want to avoid around them. You see the targets put in by global gradient, so the target is somewhere here. And so when you're starting somewhere up here, you go downhill, but you don't go up these maxima. And I'll show you a little bit later people who do really vehicle control with functions like that. So they make an interesting analysis. It's partly flawed, actually, but still very useful. I'll point that out later. An analysis of what happens in a system like that. So, it is planning. So here, this curve here, I'm tracing this out, this more complex curve is a typical result of the agent. Actually, I went through it backwards. This is the beginning of the path, and then it will be going around here. These dots are obstacles. This radius gives some sense of how broad they are in terms of the model, and here's the goal. And so what you see, of course, is that there's very short range action of these obstacles. So you're going toward the target, and then as you're entering, as you're starting to feel it going uphill, the vehicle turns relatively strongly. And so you see it's quite an articulated path. And as a contrast, there is here the path that the attractor dynamics approach generates under these conditions, which is much smoother. This is their approach, which has the second order term, the damping term. And so it's somewhat fundamental. Later discussed in the paper, this fact that these trajectories are so strongly bent have to do with the fact that it only depends on position. So when you have this dependence on turning rate on heading direction, which is sort of the angular aspect of velocity, right? Heading direction is the angle of the velocity vector, or even the second order equation, which is even one derivative higher, then that means it's somehow more, it's almost predictive. It's anticipating that you want to turn away from the obstacle, for instance, before you necessarily have gone close there. It was a question of how you scale the distance term, how early that influence is felt. And that makes it easier to already adjust your path early to avoid making these sharp turns as you come to the obstacle. They discussed that a little bit. So that's just the same analyzed a little bit differently. This is another example where they here have different, this is when they model this force state a little bit sharper, and they have tried a different parameter values. So yeah, let's discuss that. The attractor dynamics approach has to have the right parameter values, of course, to really avoid the obstacle correctly. But you see always this relatively sharp turning. It's another subtlety that in the attractor dynamics approach, we discussed it, that you don't want to avoid any obstacle that is behind you. So when you're turning away, even though you might still be close to the obstacle, you're no longer influenced by the obstacle. And that's easy to express in heading direction space, right? Because you can tell whether you're turning away or not, or you're driving away from the obstacle. While in the potential field approach, you just know where you are, and there's always this repulsive force from where you are. Even if you're already heading away from the obstacle, you will keep being pushed in that direction. Essentially, in terms of the gradient, there is a repulsive force that is being felt as long as you're within the range of the obstacle. So you want to have a large range so that you don't make these last minute maneuvers. But when you have a large range, that means you're still influenced, even though you're heading away from the obstacle or heading sideways. It's less sideways. So that's also a drawback. And then they discuss the two ways of how these approaches can fail. So the potential field approach has this problem that is sometimes called spurious attractor problem. So here's an example. There are multiple obstacles, point obstacles. There's a target, you're moving here across, and then what can happen is that you sort of get caught here. That is, you will be sort of circulating before these obstacles. You can imagine how that happens. You can think of this potential field to be sort of a landscape, and there's a big valley that leads to the target, and then you have these small hills, and you have a big valley and some small hills that can be like a mountain lake right in front of these hills as part of the big valley. And that is actually somewhat generic, and even some proof mathematically something about how likely that is, and it's very common. In fact, potential field approaches very generally have this problem. Very typically, the obstacle ones is important only when the obstacles are in the way as you go to the target. If the obstacles are off, that doesn't really matter much. So the situation where these spirit states arise, which are exactly when the obstacle is on the way down to the goal, these spurious attractors occur. So many potential field implementations that are being used have some special purpose mechanism for how to deal with that. Some approaches do that by integrating ahead of time and finding in simulation that there is some state where you get stuck, detecting that, and when they detect that, changing parameters or adding an additional force to get you out of that state. In reactive approaches, there are approaches that really, in real time, where you actually you can't avoid it beforehand. You go there, and as you notice just by sensory information that you are not making any progress, and then they add some intermediate target via point to get out of it and so on. So there's some ad hoc workarounds for that. So this arises because the potential field approach generates the behavior as a transient, right? You're going to the goal. The goal is this minimum. That would be an attractor, mathematically speaking, right? At the minimum, the gradient descent leads you to an attractor. The attractor is not the movement. It is sitting there, right? It's posture, sitting in the target. And while in the attractor dynamics approach, remember, you're sitting in a attractor all the time, and you're tracking the attractor. As you move, the attractor changes, shifts due to sensory inputs, and then you're tracking that. And so that means that for the dynamic systems approach, we really only need to make sure that the attractor states satisfy the constraints, while for the potential field approach, we need to ensure that all transients satisfy the constraints. And that's a much harder problem. So there are, if you were to start here, for instance, you would go to the target just fine. But there are just some initial conditions from which you end up in this spurious attractor state. So it's a much harder problem that is not generally solved. In the attractor dynamics approach, there is also the possibility for spurious attractors. They are not spurious in the same sense, And so here's an example of this path 2, which actually collides with these obstacles. And that really has to do with the fact that the individual contributions, when they are summed, don't guarantee that the attractors that emerge from that don't violate the constraints. And in fact, I'm not sure that you read that paper, but we discussed it in an earlier paper. So these authors actually could have known a little bit more about that, but somehow they didn't recognize that. So we actually, when we first published our approach in 82, I believe, or was it 92? I think 92, yeah, sorry, 92. With Michael Duse, we actually were aware of this problem. In extreme form would arise if you have a lot of obstacles on the left, let's say, and a lot of obstacles on the right, and you have the target right through those obstacles, and you put just a small little obstacle in the middle. Then you could see that the ones on the right push you to the left, the ones on the left push you to the right, and that can make such a strong attractor in the middle that this little obstacle, the one contribution, doesn't overrule it. And that will be a spurious attractor that is you're not supposed to have. It's actually more a constraint violation. It's not so clear if one should call that a spurious attractor. And so the authors discuss that in terms of cancellation. That is, the two obstacle avoidance terms cancel each other's influence. One pushes to the left, the other pushes to the right. The net effect is just staying in the middle. There is actually a solution to that. And that's a solution we proposed in our initial paper, which is really to reduce the representation of the obstacles. That is, which obstacles are you going to take into account, to reduce that so that you only take essential ones into account. You could say the only essential ones are the ones that you're close to. So when you're moving in here, you're going to no longer take into account all these other obstacles and that one. You're only going to take into account these two. And that's what you design to have the right bifurcation so that you're not driving through those two. That's actually the question someone asked initially about whether it's a heuristic approach. Well, it's not exact, but it is a good heuristic because we actually design to avoid collision between two obstacles that are symmetrical. That is, it's certainly designed to avoid a single obstacle. And then the cancellation could be when two obstacles push against each other, and we design that bifurcation that doesn't happen or happens in the right way, that they only allow cancellation if you do fit through these two obstacles in the middle. And then that solves that problem. So we don't actually really have that problem in the approaches that we use. In the subsymbolic approach, we don't need to tinker with that representation because the sensors themselves are a sampling of the environment. And so the sensors themselves will not repel more strongly when there are multiple obstacles here, for instance, on the left. They will just have a unit of repulsion from any obstacle on the left and corresponding on the right. So, but it's in principle, it's a problem. So I already hinted at that. The other criticism they make of the dynamical field approach, the attractor dynamics approach, is that there wasn't any real concept for the width of the obstacle. That isn't really true. I don't know why they didn't know that. And you've thought about that in the last exercise, that how we can take the width of an obstacle into account. For instance, in that case, it's done for the width of the sector, but you could, of course, do the same for the width of the obstacle. Good. So these limitations, the spurious attractors and constraint violations, are known. I hinted at the workarounds. The practical workarounds are ad hoc solutions. There is an exact workaround. It's something called an approach which uses navigation functions. And that's an approach where you make sure that the potential really only has maxima where it's supposed to be and has minima at the target. And for instance, the Poisson equation that I was mentioning, some of you who know electrodynamics and physics, right? Electrostatics actually might know that the electrical potential has a maxima at positive charges and minima at negative charges, and only there. And so by putting charges at your obstacles of the two signs and negative charges at, let's say, your target, and solving the Poisson equation, then you have a potential. Right? You can see immediately the drawback of that, because this now means that you have to solve that partial differential equation so it's a global thing, right? For all your obstacles. So in other words, the potential will depend on any obstacle. If you add an obstacle, you have to change the potential everywhere to make sure that this is true. So that's computationally costly. It's also only possible if you have global information. At every moment in time, you have to recompute that. There are approaches like that, and they simplify the computation in that you're only computing the potential near where you are, but you still have to take into account the contributions of all the other places. But you only solve the partial differential equation somewhere in some local subspace. Still, it's not really a practical approach. It's, to my knowledge, not really used in any real implementation. It's been done in laboratory implementations. Maybe there is someone out there who uses it in practice. I'm not aware of that. So, but still, so the potential field approach as a heuristic approach works quite well. It's being used a lot because also simple to understand. The attractor dynamics approach is a little bit more tricky to understand, so it's not used as much, unfortunately. I want to point to some work that my former student, Estela Bischu, and actually Wolfram Erlang was also a former student. She's in Portugal and heading a big team who developed this much further than we have. And it's really great work, which is published a few years ago. You don't have to read the abstract, just want to point you to this. Last year, I asked people to study this paper as an exercise, but it's quite complex, so I'm not recommending that. But if you want to look up that paper, I'll be happy to put it on the webpage just as reading. It does give a very good review of the attractor dynamics approach, but it then becomes much more complex. And so what they do is they look at two cooperating robots. So here's a robot platform. It's essentially the Marseille kind of robot that I showed you, just beefed up and not better. But in logical terms, it is that kind of system. And there's something mounting on top so that it can carry a platform. And this is the second one of those. And on that platform, they can actually carry some cargo. So now the effective robot is this longish rectangle. And so it's a framing as cooperative robotics, but it does solve the problems that I was hinting that the potential field approach can solve, namely making sure that this whole configuration of the cargo avoids collision as it goes through, right? And you can see that there are these problems that you have to orient in a particular way to get through a narrow opening. It's more than just a circular robot. So again, this is the complex, but it's all dynamic systems. This is their more advanced platform. On top, this is purely passive. There is some way of how the cargo is loaded up there that rotates, so it doesn't. It's just when the robot rotates, the cargo. It can rotate under the cargo. It just has some joint here, and that's just a passive joint. And other than that, these both so-called helper and leader robots are the kind of robots that we've been looking at. That is, robots that can turn on the spot. These are the wheels, and I can turn on the spot. All kinds of variables you have to think of and not go into the details. But it's really just using the distance sensors the same way we talked, right? It's very low level. And just a hint at how it works. So it does do the usual target orientation for, like if there's a target, you would have the target acquisition term that we have, an attractor at that direction. And the helper robot has a attractor. For the helper robot, the leader robot is the target. So it follows the leader robot. And then there's obstacle avoidance for the helper robot, and for the leader robot is obstacle avoidance. And they now have done some special tricks of how to not cut corners, right? You can imagine that would be sort of the problem, that the system might cut corners and then would collide. And actually humans who transport something cooperatively sometimes do run into that problem. And so they have some ingenious way of how to say that under certain configurations, so measured by the system comparing the angle to the target and the angles to obstacles, using the sensor information of the distance, to detect situations where they would be pushed if they were to go too close in our usual way. If this was a robot by its own, it would sort of find the way around here. But that wouldn't be good because the cargo would then collide with the obstacle. And so what they do is they compute a virtual target that adds up these angles in a certain way so as to take a wide turn and head in that direction. And then once it has cleared the obstacle, the computation will abandon this virtual target at some point, and then it would turn to the real target. And there is a similar thought for the helper robot. The helper robot will also detect that there is a collision danger, that it would be heading too much toward the real target, and it is being pushed away from the obstacle again by a virtual target that is in sort of the opposite direction of the obstacle. And all of this is based on geometrical analysis of hypothetical obstacles and targets, and it's for the obstacle, it's really just based on the sensory measures, on the distances, so that it's an obstacle, a wall-like obstacle. It's just computed from two neighboring values of these distances sensors. Any pair is analyzed that way. And so if they have somewhat similar distance measures, that represents effectively something like a wall, and then you compute that virtual target. So it's a lot of formulas, but they're all just simple geometrical analysis. And this system can really move through. Here's the helper and the leader, and they can go through a narrow opening. This is an example where there is a moving target. It's a track a moving target as they go through. And it all amounts to finding the attractor. I don't even know exactly which is the significant attractor here. And for instance, here for the helper, there is the attractor is here. For the leader, the attractor is somewhere else. And the paper beautifully analyzes the dynamics that result from that. Here's an example of them implementing this it's actually a German company in Guimarães in Portugal, or in Braga, with whom it's Bosch who have a factory there, and they collaborated with them in factory floor settings. So they actually had the system avoid even moving obstacles, and then moving through a corridor, going around a corner, and so I have some results in that paper. Really beautiful work. I'm very proud of that. I didn't contribute it. I'm proud that my former students are so good. Good. Okay, now maybe one more approach. I'll explain a little more technically, and then the rest of will be a bit more macroscopic. So the Borenstein-Koren is an interesting approach. It dates also from the late 80s, 90s. So it was about the same time we started. I wasn't aware of it for a while. And it's sort of like the attractor dynamics approach. Only in hindsight did I actually recognize that. It has really two components. So the vector field histogram concept versus the virtual force field concept. So the virtual force field concept is really what is sort of equivalent to the attractor dynamics approach. It's just mathematically not framed exactly that way. And that I'll explain first. The vector histogram concept has to do with the fact that they used sonars, ultrasound, which is a cheap sensor and still calibrated sensor in the sense time of flight, right? Sound, and so that's an attractive low-level sensor. It has this one drawback, that sound is reflected only from surfaces when they have the right angle to the vehicle, and therefore they are not really reliable. As online sensors, what you have to do is accumulate information as you drive around, and the angle that your vehicle has or the emitter has with surfaces varies. Then you can register surfaces and you make a map of the surfaces. So sonar always involves this mapping. And so the vector field histogram concept is sort of a really low-level way of doing the mapping. We, in our first paper with Michael Dose, actually did something related, and this is what I was hinting at, that we were representing obstacles. So we were selecting in a grid of world's grid points where there would probably be an obstacle and just selecting a subset of those. And so that's sort of related to this vector field histogram concept. So it is about detecting free directions. And I'll maybe just show you. So for instance, here you have the vehicle moving, with the sonar, it's looking here in a particular direction, and it will be accumulating ultimately information about pixels in the world where there might be a surface. For instance, under these conditions, it might enter here a reading, and then as it moves along and has gotten an echo from this object, it would add readings, for instance, at that distance and these different angles, and that would be what contributes to its represent a histogram of how often there is evidence for some obstruction in a particular location in the world. So it's encodes both the direction and the distance in which that happens. So they add these histograms up, and then what they do is the path blending looks for directions with minimal counts of these. So it looks at direction, and then it looks for local minima in direction that they will go to. I have a little bit better figure here in a moment. Here, this is a good figure. This is a Koren scan. This is actually based on accumulating across multiple runs. And so from that location, as you look into 360 degrees around the vehicle, there are directions in which there were a lot of counts of surface detection and directions in which there are few counts. So if you just select directions in which there are few such counts, then you're detecting or you're going in a direction that is free, that is unencumbered. And of course, the range depends on the sensor, right? The sensor will only look this far. So when there's some stuff very far, that will not enter. So the distance dependent comes through indirectly through the sensor characteristics. So the algorithm that they have is one that selects that direction in which there's a low number of counts. So it's not exactly attractor dynamics in the sense that you're not really updating the current heading direction, with the rate of change and so on. But you could think of it that way, right? If this would be a potential in heading direction, and if you take the gradient of that potential, then that would be your attractor dynamics. Now, would have an attractor here and an attractor there. Would have repellers here and repellers there. So one could think of it as a heading direction dynamics. They didn't frame it as a dynamics. It was an algorithm that's choosing the maximum. They had some the local minimum, and they had some method that they would stick with a choice until there is strong evidence that another choice is better, and then they would go to the other choice and so on. See, they frame this here as repulsive forces, and then there is actually a vector that they add. So they extract from these histogram these repulsive forces in heading direction, and then add no, it's actually forces in 2D space, and then they add a vector to the target, and then the algorithm was resolving whether they are in conflict or not, and then it went into the direction where there was least conflict. So it is sort of like a dynamical system approach. It has these same kind of oscillations that we sometimes had, essentially for the same reason that you're not seeing when you're heading away from the wall, you're not really being influenced by this algorithm, by the stuff in the back. And then when you're turning back, you're being affected by it. But they have a talk solution to that. It's not a severe problem. It's just an example that by accumulating evidence across time, you can get essentially a world map. And for that, you have to know where the robot is at every moment in time. That is, you have to integrate your motor commands to estimate where the robot is. And then that's how you can enter the sensor signals into the grids, right? Because you have to know how far, that this is the same pixel that you made an entry earlier that your sensor is not now pointing to, right? For that, you have to estimate where you are, and they have some approach for that. Yeah, so I think maybe I'm not going to say much more about that. So this is an approach that works in the lab, and they had some demonstrations of it. For instance, something that made the press for a while is that they had a little vehicle that was used as a guidance stick for blind people. They had a patent on it. I don't think it ever became a product. it was a little vehicle, and you had a stick that so that you could sense where that vehicle is driving. And so the vehicle would be finding a collision-free path on the sidewalk. Now, it was a real-world application. So I mentioned it because it sort of anticipates this problem, essentially the dynamics idea of using heading direction. And it did not have these spurious attractor states, and it was discussed at the time that it was better than some. These are actually also the guys who found the navigation function approach to solve the problem with spurious attractors in the potential field approach, and they were proposing this as a system that has less of that problem. This is no longer really relevant in that it was quite specifically tuned to these sonar sensors, and today that's not really a sensor that one wants to use. You may know that a LIDAR, for instance, is much superior to the sonars, not only because light is faster, so you can sample much faster than sound, but also because you don't have that reflection condition, right? You can really get a signal from any surface independent of the local angle of the surface relative to your laser beam. So as a concrete approach, it's no longer valid, but it conceptually it's an early form of dynamics. Okay, and so the last comment I want to make about this whole family of approaches is that they are being used as reactive planners, very much so, and often sort of as this lowest level. So this Arkin is someone who actually does a lot for the army now, and some of these military robots actually use ideas like that. So for instance, here is a scheme where this here would be then the potential field approach. He has generalized that. He calls that a schema control. I'll show you in a moment what that means. So that uses low-level sensor information. He calls these perceptual schemata, and then he has very simple motor behaviors, and that's controlled in some way. And then everything else is a conventional robotic architecture that has planning, has a world map, has a mission planner, and you have all kinds of way of talking to that. And I can imagine, like, you can have really, like, a lot of this is very relevant for the military, where you can do relatively complex operations that then decide themselves when they have to get some new information, when to have to update their sensory estimates of where they are and so on. But the lowest level is really this reactive sensor. And so the interesting thing, they have these, they call these receptor schemata. So they also define really so special purpose sensory processes for the different behaviors rather than a world representation, which is very robust. It doesn't require complete scene analysis and so on. So I find that quite attractive, quite consistent with our way of thinking. So here are some examples of the kind of motor schemata they would have. Move ahead, move to goal, stay on path, avoid obstacle, dodge, which sort of can imagine for the military application. Avoid like a memory trace where you were, we would call it an inhibition of return. Don't go to those places again to explore better. Go to open areas, docking, which means a particular way of approaching a position and so on. And here are examples of how some of these behaviors could be implemented. So here, this is attraction to a point. This would be a vector field that keeps you on a path, a stay on path. You could have another one that moves you in the path. This is a repeller, an obstacle. This is actually sort of a repulsion just from a certain direction. You can also have an attraction from a certain direction, which would lead to docking, arriving in a particular orientation at a target and so on. So a whole, they call these schemata, but they would be essentially more general forms of vector fields, right? Again, it's always the descent, so it's the transient that is the behavior. It's not an attractor dynamics approach in that it's not sitting in the attractor that generates the behavior. So this is an example, moving along a path that works under some conditions. And they often have some form of planner. So it's not a real planner it's sort of a reactive planner, sometimes formulated as a finite state machine, where they will activate or deactivate some of these elementary behaviors, which they call schemata, in response to certain sensory conditions that they detect. For instance, if you detect that some of your bumpers did something, then you have to, I don't know, do something else. I just took that from one of their papers without tracking exactly what they do. So the design is designing this kind of thing. I want to point to some work that's done here in Germany, in Kaiserslautern, is a group around Professor Berns who have really pushed this far. This is sort of it's behavior-based robotics that they use, probably the most sophisticated form I'm aware of. So the architecture is built off elementary behaviors. This would be an elementary behavior. They have sensory inputs and generate motor outputs. So there will be an input-output function, right? And all that they do among each other is they can, the output of one of it doesn't have to be literally motor output, it can be output to another behavior. So that's where substitution or the name that subsumption which could occur, that you would sometimes replace the sensory input by the output of some other system. You can make some kind of chains like that. And then on the other hand, these behaviors can be activated or deactivated. Essentially, there is a button here for activating it and a button for deactivating it. And these behaviors themselves can also activate other behaviors or deactivate other behaviors. That's the mathematical framing. And then you can build architectures from that. For instance, to do some particular behavior, you could have follow object that, for instance, follow object activates turn to object, which activates maybe the fusion behavior. On the other hand, you could have a collision avoidance that's always active. By having this, it's always active. You always do that. And when you get some obstacle position, it contributes to the fused rotation no matter what, while this one here is, for instance, deactivated, I believe. I don't know which button it was actually. So when that is activated, it actually it provides activation into the inhibitory slot, right? This is the activation that goes into the inhibitory slot. So it turns off the turn to object if there's obstacle avoidance. So that's how you avoid cancellation, that you turn off this one when that one is on. That's sort of the way of how you think about these things. And they have a whole set of schemes that way. They can define something like priority-based arbitration, where different contributions of some desired motor state or sensory state, inputs that act as sensory states for this system are weighted in some way. You can mediate that among these, or you can do have something that keeps track of a state that then can control which of those contributes, or a winner take all. And they define a whole set of little schemes this way of how they can combine different elementary behaviors to implement some form of logic, thinking logic. So here's an example of a behavior that is built from that, where they have some fusion behaviors that combine different constraints. They have also behavioral groups, like this would be a whole subset, so something like this, but compressed into a sub-architecture. And again, the inhibition activation paths, while the dotted line are where specific information is given. The activation is just turning on and off, and then the sensory information that is handed down to other behaviors is the few dotted paths here. And they do things like make vehicles move. They even do this for locomotion behavior, much more complex kinds of behaviors. They have some social interaction component. I didn't take that so seriously, but the vehicle path, they have reasonably complex behaviors for vehicles that they generate this way. So it's quite impressive. Okay, now the last approach I just mentioned really to point at some other problems that one can also solve that we haven't really discussed. This is called dynamic windows approach. It doesn't have to do with dynamical systems. It's more dynamic windows in the sense flexible windows or so. It goes back to this famous team, Fox, Burkhardt, and Truhn when they were young men in Bonn. And Sebastian Truhn is the person who later went to Stanford and designed this autonomous car that then won a DARPA challenge. He became very famous and is now very much interested in online learning. He has started this online university. I forgot what it's called, Utron or it's a big online university thing. And Burkhardt is actually a professor in Freiburg, and Dieter Fox is, I think, in Canada. It's a computer vision authority these days. So they all became very famous. And this was when they were young men in this in the so-called Kramer lab in Bonn. And this is a really cool little approach. It's purely ad hoc algorithmic. It's cool because it tends to generate really fast movement in robots. And just points to some additional constraints. So the idea of this is that you take into account what they call dynamic constraints, which are actually still kinematic. It's about decelerations, accelerations, so on. It's not really about the physics of the vehicle, of knowing, the sensor, what kind of control sequence you have to send. But you have some ideas of how much your vehicle can accelerate or decelerate, and therefore you can take that into account and, for instance, only brake at the last moment. The last moment means brake such that you can still make the turn. And so what they do is essentially define surfaces in velocity space that are forbidden given the sensed layout. So you still have conventional sensing, some distance sensor and so on, that gives you essentially from the current vehicle point of view a contour in the world, and then they translate that given the current velocity into constraints for velocity, and the constraints computed by saying, with that velocity and that distance I sense there, can I still stop before I hit that? And there was some ad hoc strategies like circular velocities in the two velocity space. This is linear velocity and this is rotational velocity. Non-holonomic means it has a path velocity and a turning rate, and these you can have constraints for these two kind of velocities. I'm not explaining the details of that, but you have some ad hoc strategies of how to combine them. And then the dynamic window is that you're always looking for a certain set of velocities that can be reached within a fixed time interval that you set, given the limited accelerations of the robot. That's the crucial idea. And I don't have to go through the details. You can imagine some ad hoc mathematics where you're defining the different contributions are again added by contributing to a potential function, and you're finding then the minimum or the maximum. And remember, it's maybe the maximum of that function tells you what the best combination of turning rate, so turning accelerations, that will be heading, changes of heading, right? And linear acceleration, so forward velocity acceleration is. And so this is an example of a landscape like that: rotation velocity, translation velocity, and you might want to choose, for instance, values here at the top. And you have different contributions to these functions, and then combine them, and then adding them up, right, and smoothing them in some way, and then you're finding the local maximum. You see, it's still a bit related, so it's like one derivative higher. And makes essentially a theory because it takes a new parameter into account, which is this maximum acceleration and deceleration. So through that, it translates distances into desired velocities or forbidden velocities. And not wanting to go too much into that, here's an example of how it actually works. This was done with a Rhino, which actually had zoners, I believe, and also had this problem of not sensing so well. So for instance, one of these ideas was, how can I get through a door? And so the idea would be that you could drive quite fast by keeping track of whether you can still turn. And so that was something that was impressive at the time, that it could drive quite fast with that corridors to still make the turn in time. Here's an example of that. And it avoided humans, for instance, in the corridors. This was actually the main claim to fame of the system, which was Rhino, which was supposed to be a museum guide. So it was walking around corridors, very simple geometries, like just walls and nothing very major. And then interesting source of obstacle would be humans walking around here. And so it would be driving relatively rapidly around humans. Yeah, stuff like that. Okay, so that's maybe as much as I want to take from these lectures. So you see that it's a broad field, and so we are in a special corner. This corner is the one where actually human behavior lies, and it ranges from these approaches that are really using world representations and maybe even exact computations and so on, to these heuristic, reactive, sort of reflex-like contributions, and our attractor dynamics approach can also be used more in a planning-like or in a more reactive-like. So a symbolic versus sub-symbolic actually make our approach more like planning or more like reactive planning, more like global planning versus more like reactive planning. So as a reactive approach, our approach is actually quite competitive. It's not being used so much, I think, really just because it's mathematically a bit more complex to understand, and because we're not so strong in that field. So people have sort of converged on these potential field approaches because they are so easy to conceive of and to design. But I don't think that they are, actually, I think it's really clear that they are worse than ours. That's a little bit of a pity, but I'm not really a roboticist, so I didn't have the ambition to make people use it, but it has been used. So maybe as an outlook, I'm saying that, of course, there's more than just moving around in a surface, right? And when you're doing more complex things, then that really means that you're not just choosing a velocity or a turning rate, you're choosing, maybe making decisions about other things you can do, like maybe orient or act on objects, use an arm to do something, maybe say something to a user and so on. And so then you're getting into spaces that are more interesting. Some of this is called deliberative planning, which I hinted at initially. There's a whole field of how to plan events, so discrete actions that you can take and events, and much more complex state spaces. And it's actually kind of interesting for those of you who have listened to neurocomputation classes, that there isn't really a very good neurally based theory of that, right? So while planning and associated with that search in some spaces is very much part of classical AI, there isn't really an equivalent field in neural networks, for instance. Reinforcement learning is maybe what gets closest to that, but as some of you might know, it is actually quite limited in what it can achieve in terms of planning. It has very little knowledge in some sense, doesn't generalize a lot. And so it's a real frontier of research. And so that's also interesting to my group, because we're interested in cognition and how you can actually think and not just act in more or less complex worlds. So next lecture, I had the ambition to show you a little bit about the navigation problem. The navigation problem is linked to hippocampus in humans. It's known, or in actually animals, it's known that hippocampus has some role to play in spatial orientation, but hippocampus is actually also the seat of memory, in some sense. It's important for getting memories into long-term memory. And that plays a critical role in solving problems, in using knowledge to achieve outcomes. And there is some discussion right now whether, so these two functions are related, because to know where you are, to navigate, you have to use memory to essentially know where you are relative to where you were before. Like you're recognizing, this is a place I've been at, and this is the place I want to go to, and have I reached the new place, and so on. So memory and spatial orientation are certainly evolutionarily very much linked. You can say memory arose as a way of animals would be able to return to places that they don't currently see, like to return to their home base, to their nest, or return to a place where there is good food, like foraging. Not having to search each time, but can go in a directed way to a good fruit tree, or a place where there's an ant shell that you can eat the ants off, and so on. And so there is current debate in computational neuroscience that might be the lowest level substrate for how cognition emerges. In our work that I'm reviewing in the winter semester, we use spaces. Dynamical field theory is about activation over spaces, and some of these spaces could be essentially these kind of spaces on which cognition happens. And it's a bit speculative, but there is a quite a community now of researchers who are using this metaphor, looking at cognitive maps, that is, knowing where you are and where you're going, as also the way of how you plan actions in more complex ways, like, for instance, how to repair a toaster. I always take that example, right? It's a sequence of steps, and that's not just navigating a plane, it's navigating in some configuration space, but that you could potentially embed in a more abstract form of space. So next week, I'll hint a little bit at that, and the winter semester does some of that. And we have our own research agenda currently about how to plan sequences of actions for autonomous robots. Sophie Erdker, who worked in my lab until recently, she ran this course last year. She's made some contributions to that. We have an ongoing project in that direction. So I'll just say that's something that is interesting that happens. When we do that, we go beyond just navigation. So we'll also deal with reaching for objects and manipulating objects and so on. That's the second part of the course. So that's a bit the outlook. Okay, with this, I'll close